Okay, so the lecture today is going to be on Riemannian curvature tensor, as the title suggests. So essentially, I'm going to spend almost two lectures. The lecture today and then the lecture next week uh, on Riemann curvature tensor. And after that, we're going to talk about sectional curvature and Ricci curvature and see how they're important in geometry and physics and otherwise. So, so we're going to start by discussing what a Riemannian curvature tensor is, and it would help if you briefly remember what we discussed last time. Okay. So last time we had talked about Gaussian curvature of surfaces, and this was essentially a motivation for defining Riemann curvature the way we'll define today. Okay. But let me begin by pointing out that the notion of curvature that was introduced originally by Riemann was actually very geometric. And what we'll do is we'll encounter this geometric sort of version a bit later in our discussions. So right now we're going to start with a more algebraic version, see some of its properties, compute some examples, develop the theory, and then we'll come back to Riemann's version. Okay? So if you go back in history, you'll see that what Riemann had defined was actually sectional curvature. At least in modern terms, this is what we call sectional curvature now. And he didn't define anything else, or he didn't define anything which is the modern form of the Riemann curvature tensor. So the sectional curvature is an actual generalization of Gaussian curvature. So as it happens in math, a complete formal definition of the full curvature was defined much later due to the efforts of Christoffel and other people. However, as it turns out, once you get a powerful language, the modern formulation is now far removed from its original geometric origins due to Riemann. Okay, so the advantage that we're going to have is you can build a theory, prove examples, and compute examples and prove results, but it's not going to be very geometrically motivated. Okay? So having said that, let's start. Okay, so let Mg be a Riemannian manifold with the Levy-Civita connection nabla. Okay? So am I audible to everyone?
Yes, sir.
Okay. Yeah, because I think some noises are coming, so I'm not sure where they're coming from. Okay. All right. So let Mg be a Riemannian manifold with the Levy-Civita connection nabla. We define the Riemannian curvature as a correspondence that associates to a pair of vector fields. So x and y are in gamma of Tm. So they are pairs of vector fields. You define a map denoted by R for Riemann, or R for the Riemann curvature, R of x comma y. So R of x comma y is now going to be a map from vector fields to vector fields. That's what gamma of Tm denotes. So recall that gamma of Tm means smooth sections of the tangent bundle, which is another way of saying smooth vector fields. Okay. So how is this map defined? Well, we have seen this definition in the last talk. In the last talk, we didn't encounter this term, the last term, because we are dealing with x and y as coordinate vector fields, and coordinate vector fields, the Lie bracket vanishes. That's why the last term wasn't there, but you did see the first term, right? So the first two terms is nothing but the commutator of nabla y with nabla x acting on the vector field z. So you define the Riemann curvature tensor R of xy acting on z to be this vector field. So you note that the right hand side is a vector field. Okay. So this is the definition of the Riemann curvature R. The input is two vector fields and it acts as a map from vector fields to vector fields. Okay? So far we haven't said about anything about whether this is C infinity linear, meaning that if I scale the vector field z by a function, whether the function comes out. Okay, it's pretty clear in this definition that this is linear, because if I scale the vector field z by a constant, then obviously the constant comes out, because the constant when you differentiate with respect to any vector field is just 0. So this is linear, but whether it's C infinity M linear, that we have to analyze and deduce. All right. So you note that Rxy, if you think of this as an operator, this is nothing but the commutator of nabla x with nabla y, and then you subtract off the nabla of the commutator. Okay, there's a minus sign in front. That's because in the original definition we have y, x, xy, and then xy. And here, of course, when you write commutator of x with commutator of y, that's not the same. That's minus of commutator of y with commutator of x because of skew symmetry. So the minus sign is important for us, but as you'll see, this is also a matter of convention. So in some books and some authors, they do not choose the minus sign. They ignore this and they define this quantity here, in fact, to be the Riemann curvature tensor. It's a matter of convention, as you'll see, but we have our reasons for taking this to be our choice of convention. All right. So, okay, any questions? Okay, so let's see what happens. Okay, so see, if you look back in this formula here, the last identity, it's very tempting to replace the nabla with L everywhere. So that would mean that the Lie bracket of x, the Lie bracket, the bracket of the Lie derivative of x with Lie derivative of y, and the Lie derivative of bracket xy, right? So this is something all of you have seen in the differential geometry course, that a similar identity involving Lie brackets holds. Namely, if you recall, what is the Lie derivative? Well, the Lie derivative is again a map from vector fields to vector fields, but it depends on a chosen vector field. So the Lie derivative with respect to x, where x is a vector field, is a map sending a vector field z to the Lie bracket of xz. Okay? This is how you take the Lie derivative of a vector field z along the vector field x. Okay? This is the definition. So you might know from the differential geometry that the Lie derivative satisfies this formula, that you can think of Lie derivative as an operator, and if you take the commutator of the two operators, that's nothing but the Lie derivative of the commutator of the vector fields, which gave rise to the two Lie derivatives. So why is this true? Well, it's simply a matter of writing down what this means on a vector field z, and if you write it down, you'll see that this is nothing but the Jacobi identity for vector fields. Because when you act the right hand side on z, you're going to get bracket xy acting on z bracket, and if you act it on the left hand side, you're going to get two terms, and each of the terms, when you put everything on one side, is exactly the Jacobi identity. Okay, so this holds true because of Jacobi identity, but we don't have any such thing for the covariant derivative or connection. So that's where the similarity ends. So here this is 0, but if you go back, this is typically not 0. Okay, and I think we had seen in the case of surfaces why this is not 0. So this is typically not 0, and so in one way of thinking about the Riemann curvature tensor is that it's asking whether this property is true, and if it's not true, then it's one way of measuring how far this property, that this is equal to this, fails to be true. Okay, this is just a very loose analogy with the Lie derivative so far. We haven't said anything concrete. Okay, so something more concrete is along the following lines. You set x to be del by del xi, where xi are your local coordinates, and you set y to be del by del xj. So I'll be shortening it and write del I and del j. All right. Okay, so as we have seen, in local coordinates, the Lie brackets vanishes for the coordinate vector fields. So if I calculate the Riemann curvature R del I del j, that's simply going to be this commutator, because the extra term that we had in the definition is nabla of Lie bracket del I del j, but that is 0. So nabla of the 0 vector field is 0. So that's why it simply becomes this, the actual commutator of the covariant derivatives. So from this point of view, it also is a way of measuring the failure of nabla del I and nabla del j to commute. That's what the Riemann curvature tensor measures in local coordinates. If you want, you can think about it that way. This is actually what we had discussed last time for the case of surfaces, and we said that this somehow recovers for us the Gaussian curvature. We will talk more about that in subsequent lecture. Okay, so this is one interpretation of what the Riemann curvature is trying to measure. Any questions? Okay, so yeah, as we said, we had encountered this in the previous lecture in terms of Gaussian curvature for embedded surfaces in R3. Okay, so let me make a remark regarding the sign convention. Remember I said in the Riemann curvature, you can either choose it the way we have or you can put a minus in front of everything. So we have chosen the convention which is advocated by Milner and others, namely Docarmo and the book by Galot-Hulin-Lafontaine. The convention in Kobayashi, Nomizu and some of the other texts is different. And in a way, it's just a matter of taste, okay? But the convention that we have chosen has the advantage that when we calculate in some subsequent slides this quantity. So what is this quantity? These are all coordinate vector fields. You first apply the Riemann curvature R del H del I on the vector field del J. That is now a vector field. And then you take the inner product of that with del K with respect to the Riemannian matrix. So this is now a scalar. So the point is, when we calculate the scalar, this is something which depends on four indices, H, I, J, and K. And it turns out that in our ordering of choices and signs, this number equals the classical symbol RHIJK, which is canonical, no matter what conventions we use for R. So this is something like classically fixed. So it has the advantage that this matches up with this, and there are no minus signs in front, which there would have been if we would have chosen the other convention, because the other convention was minus of R of this. That means it would have become now minus RHIJK. Okay, so that's one advantage. There are other reasons for making this choice, and you can read chapter 3 of Galot-Hulin-Lafontaine where they talk about Jacobi fields and other applications of that. So it's a matter of taste, but we'll stick with what Milner advocates. Okay. All right. So I hope there are no comments on the remark. So let's take the simplest possible example, Euclidean spaces. So we have Rn with the Euclidean metric. We have the Levi-Civita connection, and it's given by the covariant derivative, and the Christoffel symbols are 0. Okay. Okay. So this is something we know because the metric actually turns out that, this is something we computed. Okay. Because the metric Gij is constant. So whatever you differentiate, you'll be getting 0. So the Christoffel symbols are 0. So if you calculate the Riemann curvature, what will happen? You'll have to calculate nabla x, nabla y of z minus nabla y, nabla x of z. Remember that the Lie bracket of x and y commute, because you'll be acting x acting on y acting on a function, but the functions are typically smooth and in particular C2. So you'll simply be calculating this part because Lie bracket of two vector fields are 0 on our end. So this is what you get. All right. So it's dx dy z minus dy this. Okay. Yeah. So sorry, I think I should take back small piece of what I said. So when I said the Lie brackets are 0, mentally I'm plugging in x to be the coordinate vector fields. So of course I'm trying to compute this for a general pair of vector fields x and y. So let's do that. So we first calculate nabla x, nabla y of z minus nabla y, nabla x of z. But remember, how do you calculate the covariant differentiation in Rn? It is nothing but you calculate d of y. This is now going to be a matrix. We saw that in the last lecture. This matrix acts on a vector that gives you another vector. Then the matrix dx acts on that vector. This is precisely the covariant derivative on Rn, which is also the Levi-Civita connection. Right? So this term is simply the first term. The matrix dx acting on the matrix dy acting on the vector z. Similarly, this term looks like the matrix dy acting on the matrix dx acting on z. But what is this quantity? Well, this is simply dx dy minus dy dx, the matrix acting on z, which is nothing but the commutator of the vector field x and y. Or the covariant derivative of this would simply mean you take d of this vector field as a matrix, but that is equal to the commutator of the matrices. That's something we have checked. Okay, so this is a connection which satisfies nabla x, nabla y, z minus nabla y, nabla x, z minus nabla x, y, z. But that is precisely the Riemann curvature tensor. So the Riemann curvature tensor is 0, identical. All right. So is this example okay with everyone? Okay. So one reason for defining the Riemann curvature R to be of this form is this example suggests that it somehow measures how far the manifold deviates from being Euclidean. So not just meaning Euclidean as a topological space, because locally they're all Euclidean, but Euclidean as a Riemannian manifold Rn with the Euclidean matrix. So now everything is in the context of a Riemannian manifold. So you are trying to measure how much M as a Riemannian manifold deviates from Rn as a Riemannian manifold with the standard Riemannian matrix. Okay. So that's one of the motivating reasons. All right. Any questions so far? Okay. So the Riemann curvature enjoys several properties, and there's actually several of them which we'll basically be discussing throughout this lecture. The first is this one. So let me pause here for a moment and just give you some time to think why this is true. So it's saying that R of xy acting on z plus R of yx acting on z is 0. This is for all x, y, and z. So in particular, you can forget the z. This is saying the operator Rxy plus the operator Ryx is identically the 0 operator. So is it clear to everyone that this is true? Or if you have any comments, or if you have your own proof of this, so why should this thing be true, that R of xy plus R of yx is 0?
They are basically a combination of Lie bracket and Lie bracket of Ix is minus of Lie bracket
Yeah,
xy.
so I mean, and they're combination of brackets, not necessarily Lie brackets, but either Lie bracket of vector fields or the commutator of operators. So they're both commutators. They're either the Lie bracket or the other one, but they both have the property that they're skew symmetric. When I switch the inputs, the sign changes, right? So like Rxy, remember if I go back this whole slide, see, and look at the last line. What is Rx? Am I audible now?
Yes, sir.
Yeah. So because I think the internet was a bit sketchy. Yeah, so if you look at this last line, R of xy up to a minus sign is the commutator of certain things minus nabla of the commutator. So when I switch x and y, this comes up with a minus sign, but the minus sign can be pulled out. And similarly, when I switch x and y, this commutator changes by a sign. So R of xy is minus R of yx simply by how it's defined. Okay, so it's just that property. So let me go back now quickly. So yeah, so I mean, there's almost nothing to show here, but I put it as an exercise for those who might be just looking at the handout. So just prove that the skew symmetry of commutator implies the above property, where z is a dummy variable, but I'm writing it with z because often we'll be using this expression rather than R of xy plus R of yx is 0. Okay. So this is true for all triples xyz. Okay, so let me state a lemma. In fact, we'll be proving something more than the lemma, but let me state the lemma in this form. You will find equivalent versions of this in Docarmo's book or in Gallot-Lafontaine's book. But let me state it in the form that Miller states it. So if you want to read it from that book, the reference is given. It's Miller's Morse theory lemma 9.1. But we'll discuss a proof anyway. So the claim is that you look at this vector field R of xy acting on z. This is a vector field. And you choose a point P in M. So the claim is that this vector field R of xy acting on z depends only on the vectors x at P, y at P, z at P. and not on their values at nearby points. Okay, that's the first claim. The second claim is that you have a correspondence, right? What is the correspondence? Well, you take x at p, y at p, z of p, you just send it to r of x at p, y p acting on zp. So this right hand side is nothing but take r of x, y, z, restrict everything to p. That's all it is. Okay. But this is trilinear. So trilinear simply means now this is a map from v tensor v to v. So trilinear means it's linear in each of the three variables. All right. Okay. So this is the claim. So the first exercise is, if you assume the lemma, then you can show immediately that the map that we really want to talk about is this map, which goes from vector fields cross vector fields cross vector fields to vector fields. And what is the map? X comma y comma z goes to the vector field r of x y acting on z. So this is really the map that we want to talk about. And the lemma actually allows you to conclude that this map is C infinity M linear in all three variables. So remember, the usual linearity in the lemma above is just linearity over R, meaning think of TPM as a vector space over R, and linearity is in the usual sense. Here, these vector fields are modules over the ring of smooth functions. So when I talk about a map, I'm saying that this is a module map, meaning that it is C infinity M linear in each of the three summands, meaning if I put F in front of X, the F will come out in front of R. If I put F in front of Y, the F will come out, and so on. So this is very unlike what happens in the case of a connection. In a connection, it is C infinity M linear in X, but it is not C infinity M linear in Y, where the connection is given by nabla Y with respect to X, right? So,
Sir,
yes.
sir, but the lemma says that it is dependent pointwise. So can we not extend this map to fiber product over TM cross TM?
Yeah, no, you can. So I mean, that's what I'm saying, that the lemma basically is a pointwise thing, but if you have a function, and if you want to show that this new map in red is C infinity M linear, it basically boils down to checking it pointwise, and pointwise you can of course do this, right? So I mean, there's just a small algebraic deduction that if you have something like this, and then as the point varies, that will imply that the exercise in red, that it's going to be C infinity M linear. Okay? It's not really a big claim. Okay? So does that answer your question?
Sir, I was saying that we can extend this map to fiber product over TM cross TM cross TM instead of all the smooth vector fields cross products. We can just take all fiber products also.
You can take fiber products. Yes. You see, the point is, see, whenever you take the, see, if it's like this, if you have, think about it this way: if you have a map from M cross N R modules to something, and it's a map of R modules, that means it defines a map from M tensor N to that, right? It's like whenever you have a map from V cross V to something, if it's bilinear, that induces a map from V tensor V to the target. But then the question is, what is V tensor V? Well, you think about it, V tensor V is precisely going to be a section of the fiber product that you're talking about. Because usually if you take sections of TM cross TM, I mean, if you look at sections of TM cross TM, sections of TM cross TM is precisely that, right? So for every point, you're getting a pair of vector fields. And here you're going to get sections of TM cross TM cross TM. And usually sections of TM cross TM cross TM is not going to be sections of TM cross sections of, because that's too big. But this pointwise thing is going to allow you to basically induce a map at the level of tensor products of sections of TM, and that is going to become I mean, what you are suggesting. So you can either think of it as a map from TM fiber product TM, but since we are talking about this in the language of modules over rings, I mean, it's equivalent to think of this as a map from M cross M cross M to M. It's R linear in all the three variables. Here R stands for the ring C infinity M. So you can think of it as a map from M tensor M to M, where by M I mean the sections of TM. And so the R linearity is going to induce this map from the tensor product. which now if you want, you can try to think about it in terms of sections of fiber products or something. But yeah, so effectively this is a much bigger space, but it induces something in the tensor product. I mean, we'll see in the proof that, as I said, we'll prove something much stronger than the lemma. In fact, we will prove precisely the exercise in red, which will imply by restricting to a point the exercise or the assumption or the conclusion in Milner. Okay? But I'm just saying, even from Milner's thing, as P varies smoothly, you can deduce this thing. So, because I mean, point being, whenever you're evaluating this, you're evaluating everything at a particular point P. It's not you're evaluating X at P, Y at Q, and Z at R. So although this is a map from three, typically a triple of vector fields, the evaluation is happening pointwise and then P varies over N. I mean, I don't know, does that clarify what you're asking, or you still have some doubts?
Yes, sir.
Okay. So yeah, so as I said, we'll be proving actually the main result, actually the exercise in red, but I just wanted to give it as an exercise because you can deduce this assuming lemma, but then we'll prove the stronger version of the lemma. Okay. All right. So okay. So what does it mean to prove C infinity M linear? That means if you scale Z by a function, then the function should come out and it should look like f R of xy acting on Z. So let's do with the C infinity M linearity on Z first. So we calculate R of xy acting on fz. Well, what is R of xy? Well, it is the Lie bracket of, the commutator of nabla y nabla x on fz plus the commutator of xy on fz. I'm writing these in two different colors so that you can identify terms arising from these two terms. So what is the first term? The first term is simply going to be nabla y acting on nabla x of fz. But nabla x of fz, when nabla x acts on fz, it satisfies the Leibniz rule, which means either f comes out, you have nabla x of z, or x acts on f and z stays fixed. So this, the two terms is simply nothing but nabla of x acting on fz. You will get a similar two-term thing coming from nabla x acting on nabla y of this, but nabla y of fz precisely has two terms of the same type, right? Okay, what about the red term? Well, the red term, again, by Leibniz rule, it's either going to be f times nabla bracket xy of z or bracket xy of acting on f times z. All right. So these are the 6 terms that you get simply by applying Leibniz rule in the input, which is fz. Okay. So now let's apply. So now what you have to do, we have to calculate nabla y of the first term, which is f times a vector field. Again, you have to use the Leibniz rule, which means either f comes out and you get nabla y nabla x z, or y acts on f, nabla x z stays fixed. So these two terms come from the first term alone, right? So make sure you understand that. Similarly, nabla y is going to act on this. And again, you have Leibniz rule because xf is a function, z is a vector field. So you get two terms. Either the xf comes out, you have nabla y of z, or you have y acting on xf, z stays fixed. So let me pause here for a moment. Are there any questions regarding what we are trying to do? We are applying the Leibniz rule over and over again, but make sure you follow up to this point, okay? Because the rest is going to be exactly the same with certain indices interchanged. Okay, so if everything is fine, let's move on to these two terms. What happens? Well, there's a minus, but then you have nabla x of f nabla y. So similarly, f might come out, you get this term, or x acts on f, you get this term. And now nabla x will act on y f z, and you get these two terms, all right? And what about the last term? Well, the last term, let me write it in the same way. I've just changed the color from this term, which was, a shade of red, to this one, which is a shade of green. It's the same term. I'm just changing colors because now it will be easy to combine terms of the same color. So I'll be combining these green terms. Okay. So it should be clear that if I combine the green terms, what should I get? I get simply f r of xy acting on z, because f is the common term. I pull it out. What's left is precisely r of xy acting on z, right? What happens to these terms? Well, you see that this term here cancels with this, right? The xf term cancels with the xf term. The yf term cancels with the yf term, right? What is left is just this yxfz minus xyfz, and there's of course the bracket here. So what we get, combining the green terms, you get this. The middle terms in each of the rows cancel with each other. I'm left with the extreme terms on the first two rows along with the last term on the third row. So it's this. But if you stare at this, you will see that the last three terms cancel, because that's precisely the Lie bracket of xy with a minus sign, and that cancels with the last term, which is Lie bracket of xy of f of z. So this is just what we wanted. Okay. So the crucial thing that you should note here, of course, this works and it's C infinity M linear, is that this term here, nabla bracket xy, was a crucial term. If this wasn't part of the definition of the Riemann curvature tensor, the last cancellation wouldn't have happened, and you wouldn't have gotten C infinity M linearity in Z. So this last term is actually a crucial term for this to happen. Okay. Okay, any questions? Okay, so this implies what we wanted. And yeah, so I already made this remark that the last term nabla bracket xy is necessary for the Riemann curvature to be C infinity M linear in the last variable. Okay? So of course, now if you restrict everything to the point P, it's clear that R of xy, xp, yp, zp is linear in zp, because it's C infinity M linear. So in particular, you can take the constant function, for example. Okay, so now what we want to show that this is C infinity M linear in X and C infinity M linear in Y. Okay. So we are first going to show that, so what we are showing implies the trilinearity. Okay. Anyway, so let's first show C infinity M linearity in X. So what do we want to show? We want to calculate this term, R of f of x comma y acting on z. So that simply is the commutator of nabla y and nabla fx acting on z plus the nabla of commutator fxy acting on z. Right? Again, there are two colors because of how the terms are going to separate. So the first term is going to be nabla y of, see here we have the advantage that nabla is C infinity M linear in the subscript. So the f can come out. Nabla fx is nothing but f nabla x. So that becomes that. Similarly, you have f nabla x acting on nabla y of z. This is just the expansion of the first term. Okay. And the last term also you can expand. If you take Lie bracket of fxy, that simply becomes f Lie bracket xy minus y of f times the vector field x. Okay. All right. So far so good. What happens when I calculate nabla y of this? Well, again, by Leibniz rule, either f pulls out, you get nabla y, nabla x z, or y acts on f and nabla x z stays alone. So this appears out of the first term. This term is the usual term, but I've just colored it green because we'll be combining the green term. So this is the same term as before. Okay. What about the red terms? Well, you see, this, what we know is that this nabla is bilinear in both slots, and it's C infinity M linear in the subscript, which means nabla of two vector fields can be written as nabla of the first vector field times z minus nabla of the second vector field times z, right? So what should happen? The f can be pulled out. What I get is f nabla bracket xy. So there's a z missing here. If you have your notes with you, just make up a note here. There should be a z here. Okay. This is nabla bracket xy acting on z. That's by C infinity M linearity here. Similarly, the yf pulls out, you get nabla x of z. So I hope this is clear. Let me pause here for a moment and just check that this is true. So there's a Z missing here. Apart from that, everything else is correct. Are there any questions? Okay. All right. So why is this f r of x, y, z? Well, if you think about it, these two terms cancel, right? yf comes with a plus and a minus. What is left is the three green terms. That's precisely f into r of x, y acting on z. So this is C infinity m linear in x. So at this point, like a lot of these things where you have to prove a lot of symmetries in 3 variables or 4 variables and so on, you should ask yourself the question whether you want to prove it again or you can use some symmetry to be done. And in this case, we have seen that R of xy is skew symmetric in x and y, right? And because R of xyz is C infinity m linear in x, by skew symmetry, we can turn this around and conclude that R of xy is C infinity m linear in y, because you can simply switch, apply the linearity in x, switch back. And if you switch it twice, you don't change sign. So that already tells you that it's C infinity m linear in y as well. You don't have to compute anything. Okay? So, okay, so before I move on, are there any questions so far? Okay, so that basically proves that it's trilinear. I mean, in the sense it's C infinity m linear in x, y, and z. So now we work locally. So we write down our x as xj del j. So xi's are also the coordinates, but maybe I should have written ai's, bi's, and ci's. But I mean, hopefully it's clear to you what I mean by this. So the vector fields x, y, and z we write down in local coordinates. Xi's, yi's, and zj's or zi's. Okay. So what should be r of x, y, z? It should be r acting on the vector field summation x to the I d by dy, y to the j d by del j, z to the k del by del k. So as I said, remember, I mean, there's already del by del xi, but I probably should have called them AJs, BJs, and CJs. Okay, but hopefully there's no confusion what I mean by this. I'm using the Einstein summation convention here as well as in this line. So this is not one single del by del j. This is a sum. So this is a sum over j, this is a sum over j, this is a sum over j. This is a sum over I, j, and k. All right. So we have seen that it's C infinity m linear, which means what? Which means I can pull out the xi's, yj's, and zk's and sum over. Right? So this is nothing but a big sum over ijk of x to the I, y to the j, z to the k, acting on r of del I del j, acting on del k. Right? So what we want to do now, well, we basically want to see what happens if I evaluate this at a point. So what should happen? Well, it should be xi at p, yj at p, zk at p, and then whatever this quantity is at p. That's what you should get, right? Yeah, so if you evaluate the expression at p, what you get is precisely what I just said. Okay, it's just this. So now you note that this quantity, the right-hand side, this really doesn't depend on the value of xi's, yj's, and zk's in any other point other than p, because what you get here is a sum over the value of these functions at p, and then this quantity is a well-defined quantity in this local chart anyway. It's a globally defined vector field on this chart, and you restrict that to p. So this is of course at p, and then whatever else that shows up here is also at p. So it's clear that it's only dependent on the values of these functions at p and not on nearby points. So that concludes the proof. Okay. So at this point, it's very natural to wonder, how is this different from the connection? Because there seems to be some sort of difference. Remember the connection, when we talked about it, when we evaluate nabla xy at p, we said that it only depends on x at p, y at p, and the derivatives of y in the direction of x at p. However, it doesn't depend on an extension of x at p, right? But here it seems it doesn't depend on any extension. You just choose xp, yp, zp, and you can define, no matter what extension you choose, you can define this curvature. So what's going on? So the remark, of course, is that this behavior of the Riemann curvature is very different from the connection nabla xy, and that is essentially because of the C infinity m linearity in all the variables of R, all the three variables. For the connection, it is C infinity m linear in only one variable. And the way to paraphrase this lemma is to say that R is a tensor, okay? Meaning that it has this linearity property over the ring C infinity m and not just over the vector, over the field R as a real line R, okay? So the connection is not a tensor, but this Riemann curvature is a tensor. Okay? Either you take two variables R of xy or R of xy times z as a three variable function, it's a tensor. So, tensors are good, right? We have seen that torsion is a tensor, for example, right? The Riemannian metric is a tensor, but not everything is a tensor. So, okay, so let us work our way through another property, which is called the first Bianchi identity. Actually, there's two of them. I may not get around to talking about the second one, or I might mention it, but without a proof. The point is, this is important not only in geometry, but it's more so in physics and relativity and in Einstein's theory and so on. Nonetheless, so let's see what mathematically this identity is. So the identity is the following. Okay. It's a very nice identity. It says take R, X, Y, Z and then cyclically permute X, Y, and Z. There will be three terms. You get R, Y, Z acting on X plus R, Z, X acting on Y. If you sum it all up, it's 0. So this should look very, I mean, in some senses looks very familiar. This looks like the Jacobi identity, but of course this has nothing to do with Lie brackets. This is just an identity that happens to be true, but it's not due to the Jacobi identity. Okay, let me just say that but the way you should think about it is, if you wanted to remember this or memorize this, then this is essentially like the Jacobi identity, but you have to put R and put X, Y, Z in the right place. That's all. So, okay. So now there are two natural questions. How should we prove this? And if the proof is really algebraic, whether there's a geometric reason for expecting this to be true, and whether there's an intrinsic reason for expecting this to be true. Intrinsic meaning, can we deduce this from some of the other constructions that you've already seen? Okay. So we're going to address all of these issues. Okay. So, but before I move on, are there any questions so far? Okay. So remember, so I kind of want to emphasize these geometric interpretations, and I personally like them, and I would like to understand them even better, because these geometric interpretations are usually missing in most textbooks. So like in the case of torsion, we spent quite a bit of time talking about how the torsion appears. Okay, it's a nice algebraic quantity, but the torsion appeared essentially due to the failure of parallel transports to commute. Of course, infinitesimally. So if you try to look at two parallel transports and try to see whether they commute, then if you expand it in terms of epsilon, where epsilon is the length scale at which you're doing things, then the first non-trivial discrepancy is the torsion. Okay. So similar to the geometric interpretation of torsion, which involved basically a pentagon or a square, if you want to find a geometric interpretation of this, there is one, but it's going to lead you to a truncated cube and a cube, because you have three variables now and not two. Okay. So I would really refer you to this link. So if you open this in the PDF, the link is clickable. So if you click, it will lead you straight there. So you'll see a picture which should be very much reminiscent of the picture that you had drawn for the torsion. Okay, very much so. But I didn't want to spend like a few slides just on that picture, because we're not going to talk much about the geometric interpretation. At the end, you have to compute certain things, and gain something out of it. So the picture is not good for computations, obviously, but I would highly recommend people to go and have a look at this. And if you followed the discussion on torsion, you should be able to follow the discussion given here. Okay? It's very, very nice and highly recommended. Okay? So you'll see a cube appearing and a truncation appearing, and there'll be a small triangle. Like in the case of the torsion, we had a pentagon, and then the pentagon was the truncation of the square, so to speak, and the small edge of the pentagon was the torsion. So similarly, here you'll get a truncated cube, and then it's like you have a cube, you chop off one corner, you get a small triangle, and that small triangle are the three terms of the Bianchi identity, and that should add up to 0. Anyway, so rather than confuse you, you go back and have a look at this link. But in that discussion, it will be clear that torsion free plays a very crucial role. The fact that this is a torsion free connection plays a crucial role. And we are working with the Levicevere connection, so it's metric compatible and torsion free. Okay, so let's get on with an algebraic proof of this. So remember, what are we trying to prove? We are trying to prove R of xy times z, or acting on z, and then you cyclically permute xyz, the three terms add up to 0. Okay? So you simply expand it out. So you'll have three terms, and so please excuse me for writing ... And I usually tell my students not to skimp on writing one single term and write ... with three terms. I did it just to fit in things within the page. Otherwise, things are spilling over in the next page. Okay? Just for aesthetic LaTeX reasons. So there are three terms here. So what about the first term? Rxy acting on z is nothing but nabla y nabla x z minus nabla x nabla y z plus nabla bracket xy acting on z. Correct? What will be the next term? Well, it will be the same thing. You just cyclically permute x, y, and z. Same with the last term. So this is the next term. You have shifted everything to the to the left. So y has okay. So you have z, y. What happened? Yeah. So y, z, z, y. Yeah. So and then the last one is this. And I've color coded them so that it's easier for you to see which ones we're going to combine. We're going to combine the two in red, the two in orange, and the two in green, and we have to reformulate the three black terms in a certain way. Okay? But I mean, this is just replacing what R of xy is from the definition. All right. Now, what happens if I combine the two red terms? What is nabla y nabla x z minus nabla y nabla z x? So remember, if I want to combine the two red terms, how should I combine them? So I'll pause for a moment. I'll let all of you think. And our connection is metric compatible. It's torsion free. You might have to use one or both of the properties, but which property is more relevant in order to combine this term with this term? Sorry. Yeah. So I think if you think about it, see, nabla y is common. So if you ignore nabla y in front, what do you get? You get nabla x z minus nabla zx. That should remind you of torsion free, because nabla x z minus nabla zx is precisely the Lie bracket of xz. That's what torsion freeness gives you, right? So what you get is exactly this. Is that clear? Okay. If this is okay with you, then you should similarly be able to conclude what is the orange term, right? What is the orange term? The orange term is nabla z acting on this minus nabla z acting on this, but that is nabla yx minus nabla xy. By torsion freeness, this is Lie bracket of yx. So sorry, that is Lie bracket of yx, and similarly the green term, if you pull out nabla x, you get Lie bracket of zy, because this is the term with plus sign, that's the one with the minus sign. So this is what you get, right? Any questions? So we have used torsion freeness 3 times already. Okay. What about the black terms? Can we somehow simplify them? Well, if you think about it, what happens to this term? the first term here. So let me just erase it. The first term here, the z stays the same. If I switch x and y, I pay the price with a minus sign because Lie bracket is Q symmetric. So that's what I do. I switch these two, I get a minus sign. I switch y and z here, I get a minus sign. I switch z and x here, I get a minus sign, right? Why am I doing that? Well, you see here there's a yx and there's a z here, and here there's a z up here, and I want it to look like yx. Similarly, there's a x here, there's a x here. This is zy. I want to look like zy, so I put. So that's what I do. I change all the Lie brackets by switching. So hence I pay the price by putting a minus sign in front of all of them. And I've again color coded them in orange, green, and red because I'll be combining the reds, the greens, the oranges. So far so good. Okay. So now what do we do? What happens to the, if I combine the two red terms, what should I get? I should be getting something, right?
Lie bracket.
Yes, if I
Yes.
combine I just get the Lie bracket of y with Lie bracket xz. That's again torsion free, right? What about the green one? The same thing, Lie bracket of x with the Lie bracket zy. That's again torsion free. Same with the orange, right? So I have used torsion free 6 times now. Okay, so what is this quantity? Well, all of you should recognize this. This is just the Jacobi identity. This is 0, right? That's it. So that's a proof. It's not that hard. It's not that bad either. I wouldn't even call it a clever algebraic manipulation. It is basically the only manipulation that you can do using torsion free, because metric compatible doesn't appear in this Bianchi identity at all. There's no metric anywhere in this identity. And so it's in some sense the canonical way to prove this, although algebraic. Okay. So yeah, so we use the torsion freeness very, very crucially, and we haven't used metric compatibility. So this Bianchi identity would be true for a torsion-free connection as well. Okay? If I start off with a Riemannian manifold and I choose a connection which need not be Levi-Civita but it's torsion-free, same proof would work. However, we do want to work with the Levi-Civita connection because we want to also have metric compatibility, and by the fundamental theorem, there is only one such connection. Hence, the discussion that we're going to have will be focused on the Levi-Civita connection. But I wanted to point this out because sometimes you do work with other connections, and this will still be true. Okay. 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 All right. So let's. So I want to give you a different interpretation of why you would expect the Bianchi identity to be true, okay, which is not the geometric interpretation. So there's a geometric picture which tells you why it's true, like in the case of torsion. There's this algebraic proof, and then there's a tensorial interpretation of why the Bianchi identity, the first Bianchi identity is true. So recall that the torsion is a tensor, and it's a 1-2 tensor. Why is it a 1-2 tensor? Well, because it takes, so what happens to a torsion? If you give me 2 vector fields, the torsion is another vector field, right? That means what? That means the input is 2 vector fields and the output is a vector field, which means if I think of it as a tensor, it's a section of Tm, tensor T star M, tensor T star M. Because the 2 copies of T star M, they're going to be forms and they're going to eat the 2 input vector fields. That's going to give me a scalar, and the scalar times the first component, which is Tm, is going to be the output vector field. So that's why it's a 1-2 tensor. Okay. So this is a 1-2 tensor for any connection nabla. Okay. It need not be metric compatible. It need not be torsion free. And it is defined in the same way. T nabla of x comma y is going to be nabla xy minus nabla yx minus the Lie bracket xy. All right. Okay. So what you could do is you could take this torsion. It's a tensor, and we know how to covariantly differentiate tensors. That was one of the lectures that we spent quite a bit of time on. So you can differentiate vector fields, you can covariantly differentiate forms, and then you can use Leibniz rule to covariantly differentiate PQ tensors. So in particular, you can covariantly differentiate a 1-2 tensor. In particular, you can covariantly differentiate the torsion. And if you do that, what you obtain is a 1-3 tensor. So again, for the convenience of for some of you, what is a 1-3 tensor? It feeds in, so it's essentially a section of Tm, tensor T star M, tensor T star M, tensor T star M. But all that means is you have to input 3 vector fields, the output is 1 vector field. And it's tensorial, meaning that it's C infinity M linear in all the slots. Okay. And this quantity is of that type, right? You plug in X, Y, and Z, and it's giving you R of XYZ plus R of YZX plus R of ZXY. And that turns out to be 0. So you have a trilinear map, right? Sorry for everything coming all together. You have a trilinear map, nabla T sigma, that is going to be a map, but appropriately tensorial. So it should really be that. So this is an exercise, and this is essentially a local computation if you want to do it that way. Show that if I take the covariant derivative of the torsion, what I get is precisely this. Okay? This quantity. So this is not that hard to check. Okay? You can simply use the Leibniz rule and you can show that this is true. So if I assume the exercise is true, which you can go back and check, why does it give us the first Bianchi identity? Well, in our case, the Levi-Civita connection has 0 torsion, which means this tensor T nabla is identically 0, which means when I covariantly differentiate this, that is also going to be 0. That means that this term on the right hand side, these 3 terms add up to 0, which is precisely the first Bianchi identity. So another way of interpreting the Bianchi identity is that if I covariantly differentiate the torsion, then it's 0. But in our case, the torsion itself is 0. So if I covariantly differentiate something 0, it's obviously going to be 0. Okay? So it doesn't quite give you anything geometric, so to speak, because the quantity you want to vary and check that it differentiates to 0 is automatically 0 in our case. So the geometric picture is still missing here. And for that, again, I urge you to have a look at the link. But this is still conceptually a nice way of remembering the Bianchi identity. Okay, any questions? I think it's a good time to pause. Any questions so far? Okay, so let me combine the 2 properties that we have shown so far. One of them was R is Q-symmetric in X and Y, and that followed pretty much from the definition. Then we have the first Bianchi identity. So let me combine all of them and throw in a few more so that we have a nice list of properties that the Riemann curvature tensor satisfies. Okay? And so this is a lemma. So the Riemann curvature R of a Riemannian manifold satisfies the first thing we have already seen, right? This is just saying that R is Q-symmetric in X and Y. You can keep the Z or you can forget the Z. This is the first Bianchi identity we just saw. Well, this is new. So this is saying you take R, X, Y acting on Z. That's a vector field. You pair it with W. So remember, this bracket here means that I'm using the Riemannian metric G. So it's usually denoted by G, but I'm denoting it by a bracket. And this is saying you take R of XY acting on Z, inner product W, or R of XY acting on W, inner product Z, they add up to 0. Which means if you fix X and Y, then it's Q-symmetric in Z and W. If I switch Z and W, then the sign changes, okay? And then there's the last identity, which I'm writing everything in the form something is equal to 0. But if you want to read it in a more standard form, this is going to say that this quantity here is equal to this quantity here. So how should you think of the last quantity? It's just saying that you think of XY as a pair that goes in R, ZW as a pair which acts in this precise way. So if I take the pair ZW and put it in R and pull out the pair XY and put it outside, then nothing changes in this evaluation. So it's just taking the 2 pairs, swapping them, and then this evaluation is the same. That's what number 4 is saying. Okay. So any questions with the properties? We'll be proving them. The first 2 we have already seen. we'll be spending some time on proving 3 and 4 and then making some further remarks. Okay? All right. So yeah, so the way I would mentally think about it or encourage you to remember this is that the first identity says, so ideally you should think of this as the big quantity R of x, y, z, w. So given 4 vector fields, you can get a scalar, and this is that scalar. Okay, that you put the first 2 vector fields in R, that acts on the 3rd vector field, and the output vector field gets paired with the 4th vector field with respect to the Riemannian metric. What you get is a function. So if you think of it that way, then it's saying that this object, which has 4 vector fields as input, is skew-symmetric in the first 2 vector fields x and y. Identity 3 tells you that it's skew-symmetric in the last 2 vector fields w and z. Bianchi identity is some sort of identity which is not exactly any kind of skew-symmetry thing. And the 4th one is saying that if I interchange x, y, and z, w, just swap them as pairs, then this quantity is unchanged. Okay, so I don't think the 4th thing has a name. So this is what it is. Okay. Okay, so let's get on with the proof of this. All right. So as I said, the first identity is skew-symmetry in the first 2 variables, and when I say this, I mean that the full Riemann curvature tensor is really thought of as a function of 4 vector fields. And when I input x, y, z, w, what I get is R of x, y acting on z dot w with respect to the metric. That's what I mean by the full tensor. We will talk about this, at length in the next few talks. But that's what I mean. The second is the first Bianchi identity. The third is skew-symmetry in the last 2 variables. So instead of proving 3 directly, I'm claiming that it's equivalent to this assertion, right? That if I fix x and y, if I put z and z, that's 0. So why this gives us this thing? Well, see, because if R of x, y, z, inner product z is 0 for all z, I can simply plug in z plus w and z plus w here. And then by linearity, I would get z, that's 0, w, that's 0, and then I get z, w plus w, z, right? This is like a usual trick that people do. When we want to show something is skew-symmetric in 2 variables and it's bilinear, you simply show that if I put the same input in both the slots, then that quantity should be 0. So then skew-symmetry follows by replacing z with z plus w, z plus w. Is that clear? So it's equivalent to proving this. Okay, so how do we prove this? So let's compute. So we want to compute this quantity. What is this quantity? Well, you simply substitute what is R of xy acting on z. Well, it's nothing but this vector dot z with respect to the metric. And I've put different colors because, again, certain terms will cancel in certain ways. So if I expand the red term, what do I get? Well, remember, this is metric compatible, right? So the red term is what? Nabla y, nabla x, z dotted with z, correct? But metric compatibility means what? It means I can think of nabla y being, nabla y is the covariant derivative acting on this dotted with z. So that means this term is one vector field, z is another vector field, and nabla y acts on the first vector field. This stays fixed. So that's equivalent to saying I look at the product of the 2 vector fields, nabla x, nabla z with respect to x and z. This is now a function. Y acts on a function simply by directional derivative. Metric compatibility says that this quantity, when I expand, is this plus this quantity, because then nabla y is going to act on the second vector because it has already acted on the first vector that has resulted in the first red term. So the 3 red terms combine to give you metric compatibility. Is that okay with everyone? This is exactly metric compatibility applied to the vector field y acting on the pair of vector fields nabla x, z and z. Okay, so I'm writing it this way. So what about the orange? The orange has the same thing. So nabla x is the one that is acting on the pair of vector fields nabla y z and z. So by metric compatibility, this would be x acting on this function plus nabla y z and nabla x acting on z. Correct? The last term is this. Again, why is the last term this quantity? Can anybody, if you followed up to this point, I'll give you a minute. Can you think of why the last term is this term? So you have to think of metric compatibility again, right? So this is like nabla of some vector field acting on z comma z. So this is the vector field that acts on a pair. So what should metric compatibility tell you? It should tell you that the Lie bracket of xy acting on the inner product zz is equal to nabla xy acting on z dot product z plus z dot product nabla bracket Lie bracket xy z. But these two terms are the same because of the symmetry of the metric. So what I get is that Lie bracket xy acting on the inner product zz is twice this term, correct? This is just metric compatibility applied to the vector field Lie bracket xy acting on the pair z comma z. So that's why if I want to find out this term, this comes with a half. Because if the half wasn't there, this term would simply have been twice of this because of the symmetry of the Riemannian metric. Is this clear to everyone? Okay. So I mean, I'd be happy to explain this thing, even the red or the orange examples, if people still have questions, because we're using metric compatibility over and over again. We have used it 3 times already to deduce the second line. Okay, so if there are no questions, let's go on to the next line. But before I do that, you should note that these two terms cancel because they come with a minus sign, and because of the symmetry of the Riemannian metric, you can switch these two and then they cancel. Okay? So you're left with 3 terms. One of them looks like this, the other one looks like this, and the other one looks like this. They all look like a vector field acting on a function. Okay. So what do you get here? Well, you can apply the same formalism, right? So if you understood what we did in the last term here, the black term, so nabla of some vector field z comma z looks like half of whatever was the subscript acting on inner product zz. So you can apply the same thing to this term here alone, right? So nabla x zz is going to be half of x acting on inner product zz, simply by exactly applying the same principle. And then y acts on that. So this is going to be half of y acting on x acting on inner product zz, correct? What happens to the orange term? Well, the same thing, because this term itself is going to be half of y acting on inner product zz. X acts on that, so you get minus half, the minus sign carrying on from there, xy acting on zz. And then the last term is just the obvious term, right? And now this, it's pretty clear that this thing becomes 0, because if you expand Lie bracket xy, you precisely get minus of the first 2 terms, and the factor of half can be taken common. Okay. So this is 0, all right? So it's pretty clear that we have used metric compatibility. So like in the last proof where we used torsion free, essentially that's the only thing we used. In this one, we have used metric compatibility over and over and over again. In fact, that's the only thing that we used. Okay. Okay. So if there are no questions, can we move on to the last identity? I think that's, I mean that's probably algebraically the more challenging one to prove so far. I mean, all these proofs are not very hard because you almost have no room. Either you use torsion free and then you're done, or you use metric compatibility and you're done. There's, I mean, no place to do some fancy maneuvers otherwise. Okay, so let me go on to the last thing then. So to deduce the fourth identity, you can look up Docarmo or any other book. I think it's essentially an algebraic manipulation. But let me introduce what's called Milner's octahedron. So it's a nice little trick, and as is the case with anything written and explained by Milner, it essentially clarifies a lot of things which even differential geometers didn't know. So this was essentially an identity which you can prove, of course, and it was proven before Milner. But this octahedron sort of explains how you could think of this identity even if we have forgotten it, or how you could recover the proof. So let's draw the picture first. So I hope all of you can see this. So this is, again, this is a picture which I've taken from Milner's book on Morse theory. He has a small, quick review on differential geometry and Riemannian geometry, and this is given there. So this is an octahedron, right? So only 4 of the triangles are colored. The other 4 triangles are not colored, so they're basically transparent or white. So you can see the 4, there'll be 2 top triangles which are colored. One of them is turquoise and the other one is orange. And then there are 2 bottom triangles which are colored light purple and light green, right? Okay, so it has 6 vertices. I've labeled them with red dots. And each vertex has 2 potential labelings. Okay? So let me introduce the color coding. So if you look at this turquoise color triangle, the triangle on the top and to the right of the screen. So the vertices of that triangle are the 3 red vertices, but then associated to each of the red vertices, you'll see an expression in blue. So for example, if you look at the top vertex, the expression reads R of xy acting on z inner product w. If you look at the rightmost vertex, it's R of yz acting on x inner product w. And you look at the other vertex of this turquoise triangle, it's R of zx acting on y dot w. Is this, I mean, can everybody follow what I'm saying along with the picture? Okay. Yes. Okay, so the color coding is as follows, that every triangle has a particular color, and then the vertices of that triangle are labeled by a deeper shade of that color. So for example, if you look at the green triangle, it has 3 vertices, and each of the 3 vertices has, of course, 2 different labelings, but we'll choose the green labeling. So for example, for the green triangle, the lowermost vertex, the labeling is going to be RZW, X dotted with Y, and same with the other 2. The orange triangle has 3 vertices, each has an orange labeling. The purple triangle has 3 vertices, each has, so unfortunately this turned out to be black. This should have been dark, dark purple. Okay, so that's a small mistake on my part. So this should be dark purple, but all the others are color coded properly. Okay? So the claim is that the labels for each of the vertices, there are 2 of them, they are the same labels. I've just color coded it so that it's convenient for you to follow. So let's look at the first thing, the topmost vertex. Is it clear that they are the same labels? So can anybody think and tell me why the 2 labels for the top vertex, which is in blue and orange, the same? They look different, but why are they the same labels? So you can use the properties 1, 2, and 3 we have proven so far. So 1 says it's q-symmetric in x and y. 3 says it's q-symmetric in z and w. 2 is the Bianchi identity. So which ones are relevant for proving that the 2 labels for the topmost vertex are the same? So just think about it and make a guess. I mean, it's not too hard because we don't have too many properties to use.
Skew symmetric.
Of what? Of one of them, both of them?
In XY.
Yeah. So,
Properties 1 and 3.
yeah, good. So I think somebody is making sound. So good. I think so. If you use properties 1 and 3, meaning you switch x and y and you switch z and w amongst themselves, then both contributes a minus sign, but minus into minus is a plus. But that's precisely what you get in the orange, right? You have switched x and y and you have switched z and w. So you use properties 1 and 3 and you get that these two labelings are the same. Okay, let's do maybe a couple more and then I'll leave the rest for you to check. And it's easy. You have to basically use, okay, so what about, let's say this one, the rightmost vertex. It's r, y, z, x dot w. And that should be equal to r, z, y, w dot x. Well, that's because you can switch x and w and you can switch y and z, right? So that's again using 1 and 3 simultaneously. And you can convince yourself that in all the cases, the vertices have two labelings because we have switched using 1 and 3 simultaneously. That's the case for every vertex, all the 6 of them. Okay. So just convince yourself of that by going and look at it. You just have to look at it just for an instant. It should be clear that that's exactly what's happening and how one comes up with the labeling. Okay, so we haven't used the first Bianchi identity so far. Where are you going to use it? Well, the obvious question is why are certain triangles shaded and why are certain triangles not shaded? So let's look at the blue triangle. What does the blue triangle or the turquoise colored triangle, what are the vertices? The vertices have inner products. But see, if you look at the blue, the vertices with the blue labels, the inner product has W as a fixed vector on the right. It's only that the vector that you're dotting with W changes. So it's RXYZ on the top vertex, it's RYZX on the rightmost vertex, and it's RZXY on this vertex, right? The dot product is happening with a fixed vector, vector field W. So this triangle is shaded because if I sum up the values of the vertices of this turquoise colored triangle, I take this, I take the 3 blue labels, add them up. What should I get? See, the inner product is bilinear. So if I add them up, what I should get is something which is a sum of 3 terms dotted with W, correct? But what is that sum of 3 terms? It's RXYZ plus RYZX plus RZXY. But that is 0 because that is precisely the first Bianchi identity, right? So the 3 vertices of the turquoise colored triangle adds up to 0. And that's why that triangle is shaded and not the transparent triangle. Okay. So is that okay with everyone? So it's 0 because of the Bianchi identity. So let's do one more. Let's look at the green triangle. So what are the vertices? The vertices are labeled green. And if you look at the vertices, they are inner products of certain vectors with y. Y is fixed. There's a y here, there's a y here, there's a y here. So when I sum over the 3 vertices of the green triangle, it would be a sum of 3 terms dotted with y. But what are those 3 terms? It's wxz, xzw, zwx, right? That is again a cyclic ordering, and that's 0 by the Bianchi identity applied to x, w, and z. So this green triangle is shaded because the sum of the vertices adds up to 0. So now you get the picture. It's the same reason applied to the orange triangle, same reason applied to the purple triangle. All the 4 triangles whose vertices add up to 0 are the ones which are shaded. Is this clear? Any questions or comments? So what did we want to show? Remember, what we really want to show is that this top, the label for the top vertex, the blue label, equals the green label for the bottommost vertex. That's what the fourth identity says, right? If I swap ZW with XY as a pair, this blue label should equal this green label. But we are very far from going from here to here. All we have here is that sums of 3 in a certain sense are 0. So what can we do? We want to show that this quantity equals this quantity, right? So what you could do is you could just add up the two top triangles. You should get 0, correct? Because you're adding the turquoise triangle and the orange triangle, but each one of them adds up to 0. So what you get is 0. And then you can add up the two bottom triangles, right? The green one and the purple one. That also gives you 0. So I could take the difference, meaning I could take the sum of the value for the orange triangle plus the value for the turquoise triangle, which is 0, minus the value for the purple triangle minus the value for the green triangle. That is also 0. So I get 0 on the one hand, which is not giving me anything. It might seem like we're not doing anything. We're just adding and subtracting zeros. However, if you literally add the two triangles on the top and subtract the two triangles at the bottom, what do you have? See, the two triangles on the top will have the two vertices in the middle, here and here. We'll have all the 4 vertices in the middle exactly added once and 2 copies of the top vertex, which has the label RXYZW. If I subtract, if I add off the two bottom triangles, what do I get? I get the 4 vertices and then 2 copies of the bottommost vertex. So when I subtract the 2 top triangles from and the 2 bottom triangles, the 4 vertices in the middle cancel. What I left with is 2 copies of the topmost vertex minus 2 copies of the bottommost vertex. But that is 0 because I'm adding 0 plus 0 minus 0 plus 0. So that says that 2 times this quantity is equal to 2 times this quantity. Is that clear to everybody? I mean, if there are any questions, just just run it through your head. I'll pause for a moment. Just let me know if anything is unclear about this. So it also makes very clear how you are getting these two values to be the same. You simply add up the 2 top triangles, subtract the 2 bottom triangles. Algebraically, they are 0 plus 0 minus 0 plus 0. So it's 0 on the one hand. On the other hand, if you simply think of them as sums of vertices, you're left with 2 copies of the top vertex minus 2 copies of the bottom. That is 0. So the top vertex must equal the bottom vertex. That's it. It's a very slick and elegant proof. Although if you were doing the proof as is done in Locarno using algebra, you'd be doing the same proof. But it would just be a bunch of algebraic manipulations and sort of clever identifications. It wouldn't be clear why this proof could even work. At least it wasn't clear to me until I read this from Milner. So, and it's a very nice picture to take home as well. Yeah, so as I said, the vertices of each of the 4 shaded triangles add up to 0. Add the 2 top shaded triangles, subtract off the bottom 2 triangles. On the one hand, we get 0. On the other hand, we get this. So this completes the proof. Okay. So we have seen 4 properties. Apart from the first Bianchi identity, the rest you could call it the symmetry or the skew symmetry properties of the Riemann curvature. Okay, so since we have been talking about this object R, X, Y, Z, W as a gadget which takes 4 vector fields and outputs a scalar or a function, it is natural to consider the 0-4 tensor. So remember, this is a 0-4 tensor because it feeds in 4 vector fields and gives you a scalar valued function. So that's why it's a 0-4 tensor. It's a section of T star M tensor T star M tensor T star M tensor T star M. So it's given by this formula, obviously. We'll also denote this by R. So we'll be making a lot of abuse of notation. R stands for the original R of XY. R will also stand for this. So this is now going to feed in 4 vector fields Wx. So now I'm writing it in the alphabetical order. Wx, yz, and R of Wx, yz is defined to be this function. Take R of Wx acting on y dot product with z. So just a point to note, if you are following Gallot, Hulin, Lafonte, or maybe other books, they want to keep x, y here. So the natural follow-up that goes here is z, and there's nothing after z. Well, there's a if you go by cyclic ordering, but you do not want to put a as a vector field. I mean, a is already overused as it is. So they put t here. So the usual notation they use is x, y, z, comma t. And the formula is the same. R of x, comma y acting on z dotted with t. But I've chosen to use this because at the end, when you compute, you'll be computing things locally anyway. So this is just for definition. So as before, you can show that this is a tensor, meaning that it's C infinity M linear in all the 4 slots. All right. Okay. So any questions? So I want to spend a little bit of time, maybe a few minutes on making some remarks, and then we'll stop. So far we have only talked about some of the key properties of the Riemannian curvature tensor. So usually when people talk about the Riemannian curvature tensor, they talk about this quantity, this full 0,4 tensor. Okay? And it depends on what you want to compute, but the original definition is R of xy acting on vector fields and giving you vector fields. You can generalize it to a 0,3 tensor, or a 1,3 tensor, which is R of xyz. And this gives you a 0,4 tensor by pairing R of xyz with a vector field t. So the point is that this is a quadrilinear form, right? So when you restrict this to any TPM, what is this? This is a map from TPM cross TPM cross TPM cross TPM, 4 copies of it, to R. And because of the tensorial property of R, this is actually a quadrilinear form, meaning it's linear in each of the variables. As a vector space, it's a map from TPM 4 copies of it to R. It's a quadrilinear form, and I mean, most of us probably haven't encountered quadrilinear forms for all practical purposes in our mathematical lives. And quadrilinear forms are very complicated objects. Okay, so the conclusion at the end of the day is that Riemannian geometry cannot be very simple because it involves in particular this tensor, and this tensor even at a particular tangent space is a quadrilinear form, and a general quadrilinear forms are very complicated algebraic objects. Yes, even bilinear forms are, I mean, a lot has been studied and a lot is known, but then, probably we can deal with bilinear forms, but quadrilinear forms are just enormously complicated. So, however, it shouldn't be a cause for despair. Okay, we'll hopefully make some more uplifting remarks as we move on. But you cannot expect Riemannian geometry to be just a very simple thing, simply because this gadget appears naturally and this is algebraically a very formidable thing. Okay, so as I said, I mean, quadrilinear forms are hardly encountered in mathematics. So that's already a big sort of sign. However, this Riemannian curvature tensor, the full 0,4 tensor, is not an arbitrary quadrilinear form. It enjoys a lot of symmetry, as we saw. It enjoys 4 different symmetry properties. We'll see some more. So in the lemma, we saw 4 of them, right? So let me give you a small exercise, and I think it's a nice counting argument which all of you should go back and try. So forget TM, forget a quadrilinear form, or forget the Riemann curvature tensor. Let's focus on a particular vector space TPM. Now TPM is simply going to be some Euclidean space Rn. So let's even ignore TPM, let's look at Rn. So let's assume that Q is a quadrilinear form on Rd satisfying the lemma. Satisfying the lemma means what? It's a quadrilinear form on Rd, which means it's a map from Rd cross Rd cross Rd cross Rd to R. It is linear in each variable as a vector space over R. and it satisfies the lemma, meaning it satisfies the four quantities, so four properties. It's q-symmetric in the first two, q-symmetric in the last two. If you switch the first two with the last two, swap them, there's no change, and there's there's the Bianchi identity, which is some sort of a cyclic symmetry. Okay, so Q is q-symmetric in the first and last two variables and satisfies Bianchi identity and 4. So is it clear what I mean by a quadrilinear form satisfying the lemma on RD? To satisfy the four properties of the lemma, there's no R there, but you replace R with Q, W, X, Y, Z. Okay. So then there's a small exercise for you. We want to count the number of such forms. We'll call such a form curvature type because of the motivation coming from Riemannian curvature. If you take the Riemannian curvature restricted to TPM, you get precisely a quadrilinear form of this type. Right? We'll call such forms curvature type. So you can show that the curvature type quadrilinear forms a subspace of all quadrilinear forms, and the dimension of this vector space is d square into d square minus 1 divided by 12. Okay. So just a second. Yeah. So sorry about that. So, so is the statement clear regarding what these quadrilinear forms on RD are and what the exercise is? Okay. So, so this is, I mean, it's essentially saying that you want to choose a basis and then you want to compute this on a basis, but there are lots of symmetries. So if you use the symmetry and you see why the 12 appears or what actually happens, you can just compute this and check this. But let's just see it for dimension d equal to 1. So for d equal to 1, of course, you get 0. But that's simply because in dimension 1, the only, if you, there's a basis consists of one vectors. So when you're calculating this q, x, y, and w, x, y, z, the only vector that you can put is q, v1, 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 up to scaling. But then that is automatically 0 because of skew symmetry in a lot of variables. Fine, so that is obvious. So what about d equal to 2? What do you get here? You get 4, which is d squared, into 3, which is d squared minus 1. So 12 by 12, that is 1, correct? So it's saying that a quadrilinear form on R2, there's a one dimension worth of such things. So if you start off with R2, you can choose a basis E1, E2. Then a quadrilinear form on R2 is characterized by Q of E1, E2, E1, E2. That's my claim. Because if you have E1, E1, that's 0 by skew symmetry. If you have E2, E2 somewhere, that's 0. But the only time you can have a non-zero thing up to a sign is Q of E1, E2, E1, E2. Okay? And the Bianchi identity tells you how to compute the other ones. If you have something like E1, E2, E2, E1, you can just switch and make this change. So it's effectively determined by the value at E1, E2, E1, E2. Hence, it's dimension 1. Okay, is that clear? So this should tally up with how you calculate Gaussian curvature for a surface. If you were on a surface, M is a surface sigma. Look at TPM. TP sigma is a copy of R2. And then this Riemann curvature is determined by simply R1212. So you choose an orthonormal basis, del by del xi, del by del x1, del by del x2, and then you calculate R of del by del x1, del by del x2, acting on del by del x2, dotted with del by del x1. And that is simply going to be R of 1212. And that is the only curvature that exists for a surface. So that is the Gaussian curvature, and that's it. So it tallies up very nicely with all the classical things. Okay. So are there any questions or comments before I finish? Okay, so try this exercise. So I mean, this exercise is taken from Berger's, like Marcel Berger's classic, A Panoramic View of Riemannian Geometry. And if whatever we have been discussing in the past 5 minutes were a bit scary for you, don't be afraid. Let me quote a very apt uh, line from Berger. So what he says is, do not despair if the curvature tensor does not appeal to you. Okay? It is frightening for everybody. We hope that after a while you'll enjoy it a little. So, I mean, I couldn't have said it better myself. So hopefully next time we'll continue talking about Riemann curvature tensor. We'll compute things locally in certain nice coordinates, and we'll see some examples and applications so that you'll get a feel for what this thing actually is by means of computation. But the abstract entity on its own is algebraically a bit formidable. So hence we have to come up with other kinds of curvatures which one can tackle, compute, and still get some information out of those rather than dealing with this whole 0-4 tensor. Okay. So are there any questions? Okay, so let's stop here.